guys, nice to see you. Hello, how are you doing? Already tired by the end of the week, so we will try to not to put too much. Right. So let us first recall what we considered last time, and as you may remember, we were working with oscillations. In particular, we're trying to understand what is the time dependence of kinetic and potential energy of simple harmonic oscillation. And we figure out that these are some functions of time. We derive the equations. Both of them means that they change similarly to position of the block which is attached to string over time. But what is the most important that if we add up these two components, kinetic and potential energy, and get the total mechanical energy, it will be a constant parameter, which is determined by, and what actually defines the maximum mechanical, like the total mechanical energy of the block string system during oscillation. Any suggestions? We had this statement that the total mechanical energy, which remains constant, is equal to the maximum potential energy of the system, which, for instance, initially we provide to the block when we disturb it from equilibrium condition to some maximum displacement, means when it reaches amplitude value of displacement, and then let it start to oscillate. So at this, for instance, moment t equals 0, it has, the system possesses maximum potential energy, and that will define at any moment of time the total mechanical energy of the system. So taking this into account, we can use this fact for our advantage and, for instance, determine velocity of the block at any position, at any displacement, means at any moment of time. So that is quite nice, because otherwise we would need to go for this straightforward approach with kinematic equations, and there we need to take into account time and position dependent spring force which is exerted on the block. So that will be quite a challenging task. With the concept of total mechanical energy, we can do this quite easy, and we have shown that. So also we introduced two examples of simple harmonic oscillators besides string block system, and one was mathematical pendulum and another was physical pendulum. So mathematical pendulum is a rope which is considered to be massless and not stretchable, with attached some small heavy object to its edge. So it can oscillate, and we have shown that at some conditions, when angle of deviation of this pendulum, mathematical pendulum, from the equilibrium condition is small, so it's smaller than 10 degrees or smaller than about 0.2 radians, then we can make an approximation that sinus theta is approximately equal to theta itself. We replace it in the differential equation with sinus theta with theta, and instead of having second order nonlinear differential equation, which is quite challenging to solve, we end up with second order linear differential equation, which can be solved in the same manner as we did it for string block system on Monday. So we didn't repeat it last time, because solution is the same. The only difference that we operate first with displacement over time, and second, we operate with angle over time. So by solving this equation, we have shown that the period, which is one of the key parameters of this oscillation of pendulum, is not a function of mass. So which parameters define the period of mathematical pendulum? Length and acceleration of free fall. So we have 2 pi times square root of g over L. So these are the parameters which define the period. Obviously also angular frequency and frequency of mathematical pendulum. And another system which we considered was physical pendulum. So what is the key difference between physical and mathematical pendulum? Okay, so that all these features should be taken into account in order to know or determine the period of physical pendulum oscillation. However, as you may see, these parameters are different from parameters which we need for mathematical pendulum. So that is the consequence of the difference between these two systems. And what is actually the difference? So we have a very specific requirement to a pendulum to be called a mathematical pendulum. As I said, it should be massless rope or string, and should be small, much smaller in size than the length of the string, but heavy object attached to this edge. So that's a very clear definition of a pendulum which can be called and can be considered as a mathematical pendulum. However, for physical pendulum, any deviation from this condition makes any pendulum already not mathematical but physical pendulum. So means that we can deal with any arbitrary shaped body and call it, if it can oscillate about some axis of rotation, it can be called a physical pendulum. So for physical pendulum, we do not apply any restrictions in terms of its shape. So in this case, there are several additional parameters which we need to take into account in order to determine its period of oscillation. We have shown also on a quantitatively derived this equation. We got the same type of equation, second order linear equation, and got the solution for it. So we have shown that there are such parameters as mass. So we need to know the mass of the body, which we consider a physical pendulum. Then there is another parameter, distance between the center of mass of this body to the point where axis of rotation is located. And also moment of inertia of this body with respect to this axis of rotation. So now tell me please, why do we need to know the positions of center of mass and axis of rotation, means this parameter distance between them? From your point of view, what is the reason for that? So if we deal with some rigid body, which is of arbitrary shape, which is physical pendulum, we deal with axis of rotation, so there is a moment of inertia, should be known. We need to know what torque is exerted on this physical pendulum, which is the driving force for this oscillation. So in this case, the driving force for oscillation is gravitational force. And according to definition, gravitational force, like weight of the body, is exerted to a specific point, to the center of mass of this body. Then, in order to determine torque, what torque is, it consists of two components: force and what else? Force like lever arm. So we need to know both. So that means we know the weight, which mass of the block times acceleration of recall. This weight vector is exerted to the center of mass. And with respect to the center of mass, we need to know where the axis is located because we want to know the lever force. When we know both lever force and um, force, the weight, we position of the center of mass, we can calculate the torque and then proceed further with our derivation. So that's why we need to know, besides mass and moment of inertia, also distance between uh, center of mass and position of axis of rotation. So with this, we can continue further and consider oscillations already not only um, under some idealistic conditions when we don't have any dissipation of energy, but it's also possible to consider and important to consider such oscillations when we have some, for instance, drag force. Means that this block is moving, being attached to the string force. It interacts somehow with the external environment. Either it's located on some table and there is some friction, or it is immersed in some gaseous or liquid environment. Then we have some drag force, and all these factors should be taken into account because uh, that is real experience, like everyday experience. We don't observe some oscillations which just started and continues forever because energy is dissipated. So in order to take this into account, we will consider now oscillation of this string block system with exerted with some drag force which is exerted on the block. So let us consider what is the net force exerted on the block. That will be minus k times x, which is the string force, minus b times v, that is the drag force. So here we have linear dependence of drag force on velocity, means that we consider the low speed regime. Otherwise, it would be v squared. And b is some drag force coefficient, which defines the how much this block interacts with the environment, let's say with some liquid where it's immersed in, and um, it depends on several parameters like shape of the body, viscosity and density of the liquid, also surface condition of the body, what is the roughness of this surface. So there are many parameters which kind of embedded into this parameter b. And according to second law of motion, this should be equal to the product of mass and acceleration of the block. So now let us express this in means this velocity and acceleration in terms of first and second derivative of displacement over time. So let us write that minus k times x minus b times dx over dt for velocity, and m times d squared x over dt squared for acceleration. Now we divide left and right side by m and rearrange it a little bit. So we get d square x over dt square plus kx. Let us write first here b dx over dt, and then we will have plus kx. That is equal to 0. So this is a second order differential equation, but in full scale, it's a bit different from what we could see previously. So as you remember, previously we didn't have drag force, so we didn't have the contribution with first derivative of the unknown function x as a function of time. Here we have this, and this actually is a full scale second order linear differential equation. So the solution, the steps for solutions, they are similar for this particular case. We also need to write the characteristic equation. Oh, sorry, but I forgot here mass. Okay, so we write the characteristic equation b over m times uh, lambda, and here will be plus k over m, and that is equal to 0. So we have this quadratic characteristic equation. We solve this, we get equations for first and second solution for this lambda, and based on the shape of this and type of these solutions, we can determine from tables what type of functions will satisfy our condition of this differential equation as a solution for it. So in this particular case, we will get something like this. So x as a function of time will be a times exponent minus b over 2m times t times cosinus omega t plus phi. So now, if we compare this solution for displacement as a function of time to the previously derived for block spring system when we didn't consider the drag force, so that was x as a function of time equal to a times cosinus omega t plus phi. There are obviously some differences. So first difference which appeared to us is this time-dependent amplitude. So here we had constant amplitude A. In the case of the presence of drag force, this amplitude will exponentially decay over time. So that's the first key difference which should be taken into account. And another difference hidden here, this omega actually is not the same, because omega is defined. So here omega, let's call it omega naught, which, as you may remember from previous discussions, omega naught was equal to square root of k over m. And this is so-called natural frequency of the string block system. Means that frequency at which this given spring block system would oscillate if there are no any friction or drag forces exerted on it. So if we have a drag force, this frequency will be equal to square root of k over m minus b over 2m squared. And taking into account that expression, we can write that it will be equal to square root to omega naught square minus b over 2m square. So natural frequency minus some term which is determined by the interaction between the block with the environment, this drag force coefficient, and also mass of the block. So actually, the frequency, resultant frequency, will be smaller with the presence of drag force than that one which we would expect for the block string system without any drag force. So now if we want to uh, graphically represent how it will look, so we can draw x as a function of time. So this will look like this. We start from maximum displacement, which is at t equals 0. And then we get some oscillations, which exponentially with amplitude, which exponentially decays over time. So the frequency or the period, the time interval between points with the same phase, will be constant. It will not change. It will be determined by this equation. Omega naught square minus b over 2m squared, square root of this difference. However, because of dissipation of energy via this drag force, the amplitude will very rapidly decay over time. So the parameter which will make the major contribution and define how fast this amplitude decays over time will be this parameter b. So the stronger interaction between the block and the environment, the faster the amplitude of this oscillation will decrease over time, and then it will just reach to some equilibrium condition, means that there will be no oscillation anymore. So we provide some disturbance, it starts to oscillate, but amplitude reduces exponentially towards equilibrium condition. So we can write that this amplitude is proportional to exponent minus b over 2m times t. So that is the case when we once disturb the system and let it oscillate until oscillation is decayed completely because of drag force. But what if we want to have a condition for continuous oscillation regardless of this fact that we have some drag? What, from your point of view, we need to do to this system in order to keep it oscillating? External force. Okay, we need to be more specific about this. It could be just constant external force, or it should change periodically also. Also change periodic. So it should be some periodic force. And by the way, after a few minutes, we will have a chance to consider the case when, like, the difference between periodic force and constant force, what result it will have. So we will just consider different extreme scenarios. Now, let us see what will happen when, besides string force and drag force, which are exerted on the block in the previous example, we will, on top of this, add a time-dependent external force which changes periodically. So here we have some force as a function of time that is equal to F naught, means the magnitude value of the force, times sinus omega omega t. So we can pick up any periodic function. It just has to be a periodic function. That is the requirement. And in this particular example, we pick up this periodic function defined by sinus function. So now let us consider again what will be the total, like net force exerted on the block. Net force exerted on the block will be F naught times sinus omega t minus kx minus b dx over dt, and that is equal to m times d square x over dt square. So now we also can divide it by m and rearrange a bit. So it will be d square x over dt square plus k, note again, let's write b over dx over dt plus kx minus f naught sinus omega t, and that is equal to 0. So this is a bit more complicated case because it's not, yes? Again, yeah, you're right. M and M. Yes, so now we have like full scale in the second order differential equation, but also additional term here as a function of this independent variable time. So the solution of such differential equation can be represented as x as a function of time equal to a times cosinus omega t plus phi, which can look a bit surprising how simple it is. However, that is from the first point of view, because this a is not just a displacement like which we provide to the system initially, but it's a constant of several parameters, sorry, the function of several parameters. So we have f naught divided by m divided by square root of omega square minus omega naught square, and here will be plus b times omega divided by m square, and here we have also square. So now let us look at this solution. So first of all, what we see here, that this forced, so-called forced oscillation, this displacement as a function of time, will happen with the same frequency omega as the frequency of external driving force. So it means that this solution we get for a steady state condition. No matter what is the property of the uh, block string system, um, it can be any. The resultant steady state oscillation, like forced oscillation, will be with the same frequency as external force, because that is the dominant factor which will define the frequency of this oscillation. And second thing, if we take a look for expression for amplitude, it will be constant over time. So you see here we don't have any time as an independent parameter, so this will be not a function of time. So we will have oscillation, forced oscillation with the same frequency of driving force and constant amplitude, which is proportional to the magnitude of exerted force And also obviously depends on natural frequency of the system and also this drag force uh, coefficient, which defines interaction of the block with the environment. So now let us consider certain extreme cases which are interesting from our point of view in order to understand better this type of forced oscillation in the presence of drag force. So first, what we can consider, that will be omega approaches to zero. Frequency of external force is approaching to zero. So let us see here what we get. A is equal to F naught over M. Here is square root of 0 minus omega naught square, and this is second power, plus B times 0 over M second power. So that will be F naught over M square root of omega naught square in second power. And we will end up with F naught over M divided by omega naught square. So now, when we recall that omega naught is equal to square root k over m, we can write for omega naught square k over m. So we substitute it here. We get f naught over m divided by k over m. We cancel out mass and we get f naught over k for the amplitude. Now we substitute it in this expression for displacement. So x as a function of time will be equal to f naught over k times cosinus. And here we have omega t, but that will be 0 times t. So we get rid out of time dependence because we multiply this by 0. Cosinus of 0 is equal to unity. So eventually we have x equal to f naught over k. And that is nothing else as we exert some constant force to a block attached to string. Because of this external force exerted to the string, it is displaced by certain distance x, which is the displacement, and then it stays in this excited condition. So in this particular case, when the external force is applied with frequency which approaches to 0, means we apply just constant force and excite the block string system by displacement x. So it's not in equilibrium condition at x equals 0, but x is equal f naught divided by k. So obviously it has nothing to do with oscillations because it will just stay in this equilibrium excited condition forever until we don't release the exerted force. So now let us consider one more option, and we were already at this extreme 0 case. Let's go to extreme omega approaches to infinity. So when we apply external driving force with very high frequency. So let's see what we get. Let's look at this equation for amplitude. We see here that we have omega and here we have omega in the denominator. So if omega approaches to infinity, then this amplitude um, will approach to 0 because amplitude is equal to f naught divided by m, and here in the denominator we'll have infinity, which means that amplitude approaches to 0. And in this case, if we consider x as a function of time, it will be 0 times cosinus omega t, which this very high frequency which approaches to infinity. So obviously that will be 0. So regardless of the force, we can apply extremely large force to this system. Doesn't matter what force we will apply. If the frequency is very high, means much higher than the frequency, natural frequency of the system, it will not even respond to this force. So it will remain not oscillating, but moreover, it will even be at x equals 0, it will even not be excited from equilibrium condition, as opposite to previous case. When we apply constant force, we at least excite the system from equilibrium condition by displacement f naught divided by k. Here, no matter what force we apply, it, at extremely high frequency, the system will just remain peacefully in equilibrium condition and nothing will happen with it. So another interesting case which we have to consider here is when frequency of external driving force is equal to natural frequency of the string block system. So in this case, we will write instead of omega, omega naught. So amplitude is equal to f naught over m divided by square root of omega naught square minus omega naught square squared minus plus b omega naught over m square. So what we see here that this first term is equal to 0. So usually we have two terms which contribute to the denominator of this function. Here one term is equal to 0 means that we end up with a condition when we have the maximum, like smallest the denominator means the maximum value for our amplitude. So in this case we have f naught over m divided by b omega naught divided by m. So m can be cancelled out, and f naught over b times omega naught is actually the maximum amplitude which can be reached for given block string system in given environment. Because here we also, besides natural frequency, we also have the drag force coefficient. And obviously the magnitude of the force which is exerted, like amplitude value of the force which is exerted on this system. So eventually for this scenario, which is called this regime of oscillation when external driving force coincides in frequency with the natural frequency, is called resonance. So under resonance condition, we can write that x as a function of time will be f naught over b times omega naught times cosinus omega naught times t plus phi. So it will obviously oscillate with natural frequency because these two frequencies coincide, and you will reach the maximum value for amplitude. So now let us try to summarize our discussion. So we continued the analysis of oscillations, and for today's lecture, we considered the drag force first, so so-called damped oscillations. When we have a single disturbance, it causes some oscillation of the block string system, but because of interaction with between the block and environment, in particular, in this case, we consider drag force, which linearly depends on velocity. It decays over time because of dissipation of uh, energy, since we need to take into account the drag force. So, as a result for such damped oscillation, we observe some exponentially decaying amplitude. So it goes from maximum initial disturbance, like displacement of the system, and over time it decays exponentially, and we have constant frequency of such oscillation, which is defined by the natural frequency of the system, block string system, and properties of the interaction of this block with the um, surrounding environment. Means string coefficient, sorry, this drag force coefficient B. However, if we want to keep this oscillation going for a long time, we need to compensate the dissipated energy, and that is realized by performing some mechanical work on the system by external periodic force. So when we exert some external periodic force on the system, we get oscillations which are called forced oscillation, and regardless of dissipation of energy because of the drag force, we still can keep it going over time. We have shown that um, displacement as a function of time for such forced oscillation will be described by constant amplitude, which is time independent and is determined by the magnitude of exerted force and features of the system, uh, K, M, and B coefficients. And what is also important, that the oscillation for such, like this forced oscillation, will happen with the frequency of the driving force, because this is the dominant factor which will define the resultant steady state frequency of such oscillation. We considered different extreme cases when frequency is of driving force is approaching to zero, means we exert only just some constant frequency. That will result in the excitement of the system by displacing it from equilibrium condition by x equal to f naught divided by k. But there is no oscillation, obviously, because force is constant. If frequency approaches to infinity, then no matter how big force, external force is exerted, it will not oscillate, and moreover, it will not even be out from equilibrium condition, because x will be 0. And of course, resonant condition, when frequency of external driving force coincides with the frequency, like natural frequency of the system. In that case, we will observe oscillation with the natural frequency, obviously, because both are the same, and maximum possible amplitude for a given system, defined by certain magnitude of exerted force, drag force coefficient, and natural frequency of the system. Thank you very much for attention. We will continue with waves already on Monday, so I wish you great weekend and see you next week.